Okay, good morning. I hope you can hear me. Let me know if you can hear me by giving a thumbs up in Gathertown, so I know that this is coming through. I see some thumbs up, some thumbs ups. I don't know what the plural of thumbs up is. Um, Glad you're all with us again in this new year. Happy New Year again. So what we're gonna do starting today, in the next week or so, maybe even only this week, is static equilibrium problems. What we did in the past is kind of let's take a look back at the entire course up till now, and let's look at what we did. So we started off with kinematics, right? And I explained that kinematics is the study of motion without considering what caused that motion. So without considering the forces, which we now know caused that motion. So that's what we did in chapters 1 through 4. So that was things like displacement vectors, velocity vectors, acceleration vectors. Then we went to dynamics, which was chapters 5 through 9, I think. So that was relating now the acceleration to the force. We used Newton's second law for that to relate the force, what causes the motion, to these kinematic quantities, displacement, velocity, and acceleration. Then we did the same thing in rotational coordinates. So we introduced theta, omega, and alpha as the angular angle, the angular coordinate, the angular velocity, and the angular acceleration. And then in chapter 11, we related that back to the torque on an object. So this is what we've covered: kinematics and dynamics. So now what we're going to do is look at statics, which is the study of things that don't move. So now, well, things that don't accelerate, at least. So this is the study of things that have no acceleration and have no rotation. Since the acceleration is 0, the linear acceleration and the angular acceleration is 0, we can always pick an inertial reference frame where that also corresponds to a velocity that is 0. If we pick that inertial reference frame to move with the velocity, the same velocity of the object itself. Notice that we also have done this for a couple of different systems. We've done this for points or point masses. Then we went to things like collections of points, collections of point masses. And that's when we introduced, for example, the concept of a center of mass, or total linear momentum. And then we've also applied this to rigid bodies, which are fixed objects with a finite extent, where we also have to think about center of mass. So what we're going to focus on now is on this statics part, because in many cases, and in particular in mechanical engineering cases, we're going to want we're going to want things to remain with 0 angular and linear velocity. If a building has a non-zero linear or angular acceleration, then we have a problem. So that's the thing that we want to avoid, and we want to come up with some conditions under which under which we are able to talk about static situations. So what we'll call these situations are equilibrium situations, or that's going to be equilibrium. An equilibrium, or static equilibrium in particular, is a condition when as I wrote there already and introduced it, when the linear acceleration and the angular acceleration is 0 in some inertial reference frame. If I can find an inertial reference frame where the acceleration and the linear acceleration and the angular acceleration are both 0, then that object or that system is said to be in static equilibrium. If this is, of course, usually it's not going to be that hard to find that equilibrium, that inertial reference frame. If this is true in some inertial reference frame, then it's actually going to be true in all inertial reference frames. In all, not just reference frames, in all inertial reference frames. But usually, of course, we'll pick the reference frame that is most clearly associated with the object. So let's see. I don't think the slides are quite relevant yet. No. So if, for example, we're looking at a classic example, which I'm sure those in mechanical engineering will want to treat, is a cantilevered beam that's sticking out of some wall, and we're actually gonna treat this problem likely on Friday. So we'll want this to be in static equilibrium, so that will mean that we'll want the acceleration and the angular acceleration, the linear acceleration and the angular acceleration to be 0. So we're going to, of course, pick a reference frame that is fixed to the wall here, and in that reference frame we'll want this cantilevered beam to not move at all, and there will be some conditions that follow. What are the conditions? So let me erase this again. So the conditions for static equilibrium are twofold. So there's two conditions, and of course you can sort of see what the conditions are going to be. First of all, if m times the acceleration of the center of mass is the sum of all of the forces, external forces on that object, which is Newton's law for these in its most general form. If that acceleration is 0, because the linear acceleration is 0, then of course the sum of all of the forces on the object will have to be 0. So that's the first condition for static equilibrium. The second condition will of course come from the angular acceleration part here. From the angular acceleration, which has to be 0. So that, in that case, our Newton's law looks like this, where now we have the sum of all the torques that is equal to the moment of inertia times the angular acceleration. Now, since the angular acceleration has to be 0, all of this has to be 0, so the sum of all of the torques will have to be 0. So if we have some object and there's some forces working on this from a variety of different directions, F1, F2, F3, these are all vector quantities, of course, and let's say there's somewhere a torque tau 1, and maybe there's a torque tau 2, and there's a torque tau 3 working on this object here. So when will this be in static equilibrium? Well, when the sum of all the forces is equal to 0, and when the sum of all the torques is equal to 0. So when both of those conditions are satisfied. Now one problem immediately presents itself. If I talk about torques here, torque around what axis? In this case, there's, I could calculate the torque around this axis. I could calculate the torque around the axis where this force F3 applies, which would mean that F3 then doesn't cause any torque at all on this object, but F1 and F2 will still cause a torque. So it turns out it doesn't actually matter which axis you use. You can use any axis. You can use around any axis or around any pivot point or any origin of an inertial reference frame. So that of course means that as you know, in physics we are lazy, so we will want to pick the particular origin or reference frame that that causes the math to be the easiest. So if we are given, for example, some of these forces, we would probably pick the origin at the point where one of these forces applies, just so we are ending up with a zero torque for at least one of the terms. So we can choose any axis, any point of reference, and use that, any pivot point, and use that to calculate our torques around. We know for the forces, of course, that this doesn't really matter. The force balance, the first condition of static equilibrium, doesn't depend on where or doesn't explicitly depend on the position of where we pick that origin. It's only for the second condition where we have the torques, where it matters for the numerical evaluation where we pick the origin. There's one simplification of this this situation, and that's actually going to be a very common simplification, or a special case, and that special case is if all of the forces are in a plane, the forces are all in one plane, and the axis of rotation, or any rotation, is perpendicular to that plane. So in fact, that's exactly the situation I've drawn here, because that's what happens when you work in 2 dimensions. In this case, all of the forces are in this plane, and all of the torques are rotation, so they're actually perpendicular to the plane, and the axis of rotation is perpendicular to the plane. So in that case, we referred to a 2-dimensional statics problem. And in that 2-dimensional problem, the conditions become that now, well, all of our forces are inside the plane, so they're all perpendicular to the z-axis, which we'll pick to be out of the plane. So if we pick the z-axis here to be in that direction, and then x, and let me make sure I move these out of the way. So if we have our x and our y-axis in this direction, and then z out of the plane, then all of our forces are now perpendicular to the z-axis. So that means we can just write our conditions in terms of x and y components. So our conditions become that the sum of the x components of all of the forces has to be equal to 0. The sum of all of the y components has to be equal to 0. And the second condition, and of course the sum of all of the z components is 0 because none of them have a z component. The second condition is now that all of the torques are parallel to the z-axis, or in other words, the rotation is inside the plane. So in this case, since they're all perpendicular, since they're all parallel to the z-axis, there is no x and y component to the torques. So all we have is tau k z is equal to 0. So instead of having 2 vector equations here, which have each 3 components, we now end up with just 3 scalar equations, the 2 vector components from the force, and the 1 vector component, the 1 non-zero vector component from the torque. So in this case, in this very common case of 2D statics problems, we're actually going to end up with a simplified situation. But it makes sense to always think first in terms of the 3-dimensional situations. Okay, so let's look at a couple of reminders, I guess. So for the torque, so if we have, in this case, a torque that is perpendicular to this xy plane, and it is along the z-axis, that means our force will have to be in the plane. And so if our force is in this plane, that means we use our right-hand rule to indicate that the torque in this case is pointing along the z-axis. So this will be a positive torque, or the component in our scalar equation that we use in this two-dimensional problem will be positive. If we have a torque that is pointing in the opposite direction, if the force is going in the other direction here, so now our right-hand rule will give us, if you follow with your fingers from the lever arm to the line of action, then your thumb will point downwards along the z-axis here. So we'll end up with a negative torque. So if we use this component equation for the two-dimensional problems, we're going to have to make sure we use the right sign for those forces. And again, this is going to be a very common situation. I think there's maybe one problem we do in statics that involves the full three-dimensional thinking, but most of them are just going to be two-dimensional problems. So for all of those problems, keep in mind the sign that you have to use for clockwise and anti-clockwise, counterclockwise rotation. So let's look at what happens in this case for some of these problems, and the book uses this example of a truck that's tipping over. So what happens when a truck is tipping over is there's a point of contact with the road here, one of the wheels, and there's also another force that applies to the truck, and that's the combined center of mass of the load and the truck itself. And so essentially we have a mass with a center of mass, and we have a point of contact with the ground. Now I'm not going to go over this in too much detail in the context of this problem, but I'm going to I do have to point out the car is actually behind the truck, is not going to get crushed there, so don't worry about the car. It's on a side road there. Maybe that doesn't necessarily make it any better, but okay. So let's look at this actually in terms of a drawing. So first of all, let's talk about the different kind of forces that apply here, right? So let's different kinds of forces that apply. So in this problem, we clearly have two types of forces. We have a force here, the normal force, that applies exactly at one point and at one point only. It's at that tire, at the contact point between the tire and the ground. So that's a discrete force. It applies at a single point. So an example is the normal forces, or any kind of contact force. And let me actually add here, let's make this explicitly a point contact force. So it's clear that it applies at a single point. Why do I do that? Because the next kind of force will have a contact force that isn't a discrete force. So in contrast to the discrete forces, we have distributed forces. So those are forces that apply over extended objects, extended volumes, extended surfaces. And here, for example, we have the mass, or mass is not the force, let me erase that, the weight So the weight applies over the mass distribution, applies to the mass distribution. So however the mass is distributed, that's how the weight will be distributed. And we use that to determine a center of mass, which is the effective point that the weight applies at. So that's a effective location for an equivalent discrete force. But we have to remember that that's an approximation, right? Or at least that's it's a good approximation, of course, but we have to calculate that center of mass. Other examples here are pressure, and in particular, I'm thinking then, for those of you again who are going into maybe civil engineering, wind pressure on a building. So if we have a building and there's some wind that is applying to this building, now the pressure won't be applying at the center of mass, but it will be applying at the center of that surface. So that is actually going to be the center of pressure. It's also something you'll encounter in aerodynamics. Center of pressure is essentially what you would get if you do the center of mass, but on the surface of that side and from which the pressure, the wind pressure comes. And this is where, in fact, also the contact forces play a role again. So if we think back now at contact forces, certain contact forces will also apply at an equivalent point. In particular, now I'm going to call this a surface contact force, which is what you get, for example, if an object is lying perfectly flat and has contact with an extended area. So in this case, we can say that effectively the equivalent location, the effective location for an equivalent discrete force will be at the center of that surface area, whereas for a point contact here, that's what we get if we have only a single point where there is contact. Right? So those are the different forces, and I'm actually going to be using this this discrete force and the center of mass to treat this example of the truck, but in a little bit more of an abstract way. That hopefully, I mean, it won't be that abstract, so don't worry. But in a way that that is a little bit more generally applicable than just trucks. So we're going to talk about the two different kinds of stability of equilibrium. So I introduced equilibrium as the linear acceleration is equal to 0 and the angular acceleration is equal to 0. But we can have two different kinds of equilibrium. You can have a stable equilibrium. So that's an example where, or actually, let me not talk about. Well, yeah, let me introduce stable equilibrium. So that's an example where we have, for example, a mass, a block, a box that's just lying on a surface, and as I indicated, the normal force will be applying at the effective center of that surface where there's contact, and the weight will be applying at the center of mass of this object, so that will be at the center. And I'm drawing them a little bit offset, but of course the force, the normal force and the weight will be perfectly on the same line here. So in that case, this is a stable equilibrium, because if I introduce some deviation a small deviation from this equilibrium will return, or the small deviations will cause a restoring force back to the equilibrium. So what do I mean when I talk about a small deviation? Well, that's if, for example, I tilt this box just a little bit like this. So now what happens? I'm in this point contact force situation now. The normal force is like this here. The weight is still applying at the center of mass, because that's still a distributed force. The normal force is now not a distributed force anymore. It becomes a point contact force. And so with these two forces, because they're displaced from each other, they will cause a torque that is going to be pointing in this direction, and that will bring the box back to its stable equilibrium position of being flat on the floor. So this causes, so first of all, the conditions for if this was an equilibrium, which it isn't, then we would require that the normal force and the weight have the same magnitude and the torque is 0. But in this case, of course, the torque is not equal to 0. The torque will be non-zero and will be given by the weight times the distance between those two lines of action. And that torque will be, in this case, will be positive, right? It's positive because by the right-hand rule, it will be pointing out of the plane. And that will bring the box back to its stable equilibrium. So if we think about that in terms of a potential energy diagram, if this is our potential energy and this is our, I'm just going to vaguely call this deviation, which could be something like the angle between the box and the ground. So the potential energy will have a minimum at the equilibrium. That's a stable equilibrium. If I go up that hill for some reason, the equilibrium, the restoring force will want me to go back down to the lowest potential energy. Now we can also introduce an unstable equilibrium. And note that here, of course, this is an equilibrium because now the normal forces, the sum of all the forces, or the normal force plus the weight is equal to 0, and the torque is equal to 0. So in that case, we are indeed in an equilibrium. Now, there's another situation where we can draw that that is an equilibrium. That is if I put the box exactly on one corner such that the weight is pointing down here and the normal force, which is now a point contact normal force, point contact force, is exactly along the line that goes through the center of mass. So again here, the normal force plus the weight will be equal to 0, and the torque will be equal to 0 as well. So this is an equilibrium as well. But of course, what happens now if there's a small deviation, let's say I have a small deviation that that causes the box to tilt just a little bit to the right. So now my normal force is still applying here, but okay, my drawing is not necessarily great here. But the weight is now slightly displaced from the normal force. So now what will happen is there will be a torque that is created. The torque in this case will be negative. The torque is negative, which means that there will be a clockwise rotation. And we're actually going to move away from that stable equilibrium. So in this case, if we wanted to draw this as a potential energy diagram, we would actually we'd have something like this, where we start off at a maximum of potential energy. It's still flat. Equilibrium is flat that corresponds to the fact that there's no total energy, no total force on this on the box. But as soon as we deviate a little bit from that equilibrium, we're actually going to want to go down to the smallest potential energy situation if we let things move on its own. So that's an unstable equilibrium. So now we can, of course, look at when we reach that unstable equilibrium, or when we reach the limits of stability on any equilibrium. So if we have, or if we go back to our drawing of the truck here, and I'm going to take this drawing on the right here, and I'm going to reproduce it on the whiteboard. So if we now have the two tires, one tire here, another tire here, this is where the normal force will apply. And if we have on this truck somewhere there's a center of mass, let's say the center of mass is here. If the center of mass is here, under this particular tilt angle, as long as, I shouldn't draw that long, as long as the weight is applying to the left of the normal force, or to the left of the contact point, for the truck between the two tires, then there will be a torque that brings the truck back to its equilibrium, to its stable equilibrium, which is the two wheels on the ground. If the weight goes to the right, or to the outside of the two tires, so if we now have something like this, and the normal force is applying here, and the weight is now applying here, then of course the truck will tip over, and it will go to the next stable equilibrium, which is the one where the truck is entirely flat on its side. So that's not the optimal equilibrium for driving purposes, but it is also a stable equilibrium. So that's kind of what the textbook tries to explain. It doesn't do as good a job, I think, as it could. But I hope that my drawings made that a little bit better. So let's look now at a different problem, which is, again, it's a problem of static equilibrium. It's this problem where we have now, again, 2 points of contact. A point of contact at the front of the car, a point of contact at the back of the car, and we know that the total force that the car exerts on the earth is 52% of the weight is in the front tire, and 48% of the weight is in the back tires, the front two tires and the back two tires. So if we know that, and we know that the car has a length or a distance between the two tires that is 2.5 meters, can we calculate from that where the position of the center of gravity is located, or center of mass? The textbook makes some statements about, there's a difference between center of mass and center of gravity, which is apparent for non-uniformly distributed masses. I think people will use center of mass when they talk about the actual center of gravity for non-uniform mass distributions. So I wouldn't put too much stock in that particular difference. But in this case, we're going to talk about center of gravity and center of mass as being the same thing, right? So what happens if we think about the car, which in this case, is in static equilibrium? It's sitting still, or it's going at a constant velocity, and in any case, it's not moving in the y direction. So in the y direction, in the vertical direction, it's going to be in equilibrium anyway, even when it's accelerating in the x direction. But let's just assume it's standing still. Now we can draw the different forces, the points where they apply, including the center of mass, of course. And then we can calculate the conditions for static equilibrium. So even though in the previous drawing the force the weight of the car was drawn down, of course the force that applies on the tires is the normal force that's working up, right? So make sure that you have that sign correct, or that direction correct. So the force on the forward tires, the normal force, is this 52% of the weight. The force on the rear tires is 48% of the weight. And somewhere along the length of the car, so this total length is d, 2.5 meters. Somewhere along the length of the car, there's a center of mass, which is where the weight applies. So now if we know that we're in static equilibrium, we can use this to calculate where that center of mass is located. In other words, what is the distance x between the center of mass and the rear tires. Now I started off by saying we can pick our pivot point anywhere we like, right? Or rotation, or center of rotation. So we could pick it in the front tires, which is what the textbook does. We could pick it at the center of mass, which is also something the textbook does. So we're going to actually pick it at the rear. So we're going to pick the pivot point at the rear tires, calculate the conditions for equilibrium. Now, one condition is immediately satisfied. That's the force condition, because the sum of the forces in the positive direction is equal to the sum of the forces in the negative direction. So the only condition that will be relevant here, or that isn't already included by the fact that we're using 52% and 48% of the weight, is the torque condition. So we're going to use this from the rear tire. So if we have our situation here, this is the distance d, that's our force on the rear tire, 0.48 times the weight. Then we have the weight that applies here, and then we have the force on the front tires, which is 0.52 times the weight. And this is a distance x, and the total distance is d. If we pick this as our pivot point, then the sum of the torques will be, well, there's no torque from the force on the rear tires. There's x times the weight in the positive direction due to the weight at the center of mass. And then there's a negative torque in the clockwise direction. So this is a torque in the counterclockwise direction. So the torque in the clockwise direction is negative due to the front tires. So that's going to be d times 0.52 times the weight. And that will have to be equal to 0. That's our condition for static equilibrium, or second condition for static equilibrium. So now we can use that to calculate x. So x will be, well, I mean, it's a fairly trivial calculation. Our weights drop out, and we immediately get that x is 0.52 times the distance. And that is, if you look at the textbook, actually, you'll see that it does a similar calculation, but from the other pivot points. And of course, it's the same answer. We find that x is 0.52d, which is the same thing we would have found if we picked a pivot point here, or if we picked a pivot point here. So that means we can calculate the position of the center of mass from these forces at the front and the rear tire. Another example that the textbook goes through is the example where the extended nature of the object, of the mass distribution, can be ignored. So in this case, there's just a single point mass that has all of the weight that is added to this span here. And in that case, of course, the torque equation disappears. So in some sense here, we didn't have to use the force balance equation. The only thing we had to use was the torque. In this case, and we can actually go to the free body diagram. In this case, we can actually ignore the torque equation, and the only thing that will be relevant is just the free body diagram of the mass itself. And this is actually the kind of problem that we could have solved already in chapter 4 or 5. So this is something that is going to look familiar, and the only thing that makes it complicated is that you add some trigonometry to it to introduce those angles. But you'll see that in this case, this is just a simple free body diagram problem. Okay, so we're going to use these concepts of static equilibrium being contingent on two conditions. The sum of the forces has to be equal to 0, and the sum of the torques has to be equal to 0. So we'll use that on Friday to do some other examples of static equilibrium that are going to get us closer to for example, civil engineering or other kind of mechanics calculations. Okay, talk to you on Friday.